Welcome to today's presentation, Essential Technologies for Structural BIM, helping structural engineers plug into today's BIM workflows. My name's Dan Monahan, and I'm the Managing Director for Nemetschek SIA, a leading provider of 3D engineering software. For over 15 years, I've been helping firms evaluate and successfully implement AEC technology. By now, most of us have heard of BIM, or Building Information Modeling. BIM brings a promise to streamline workflows and increase efficiencies. But what is BIM? What impact is BIM having on today's engineering workflows? And, as structural engineers, what do we need to know when evaluating the various structural design software in today's marketplace? In this 45-minute webinar, we'll explore these questions and introduce you to the key technologies that can help engineers successfully migrate or improve their BIM workflows. Now, before we get started, just a little housekeeping. This is an approved AIA CES course. We will provide information at the end of this presentation on how you can receive your learning credits. Also, the AIA has asked that we encourage members to complete the online CES Discovery Evaluation. To complete the survey, please log on to aia.learnflex.net. To find the survey, you will need to know the provider name, Nemetschek, the course name, Essential Technologies in Structural BIM, and the course number, SIA01. And for those of you who are new to GoToMeeting, on your screen you should see the GoToMeeting controls. They should look something like this. You can minimize and expand the controls by clicking on this arrow button in the upper left-hand corner. And if you have questions during the meeting, please type your questions here in the chat window. At the end of the presentation, we'll answer as many questions as time permits. It seems we spend a lot of time explaining ourselves in this industry. BIM is a little like the fable of the 6 blind Hindustani men and the elephant. The fable goes something like this. 6 blind men walked around and touched an elephant to learn what it was like. When asked to describe the elephant, each came away with some way different idea about what they'd experienced. BIM is kind of like that. Depending on the context and who you ask, BIM can mean a better CAD technology, integrating 3D modeling, information, and 2D drawings, a better design process, better teamwork and cooperation, a better business model. BIM today is a concept that has a lot of moving parts. One of the best definitions I've heard for BIM came from Jerry Lazarin, a consultant and industry pundit. He likes to say that BIM is what any technology vendor is trying to sell you. So let's try to nail down some definitions. Unfortunately, BIM is where acronyms get us into trouble because users refer to BIM as both a thing, the building model, as well as the activity that produces the thing, modeling. For structural engineers, this means that you need structural design software that can help you efficiently create a BIM model, and you need to be able to share that model with others involved in the design and construction process. Some writers have referred to this as Big BIM or Little BIM or Social BIM and Lonely BIM. With Little BIM, we're talking about using BIM modeling to increase the design efficiencies in the firm. With Big BIM, we're talking about using that model to increase the efficiencies in the larger construction process. This concept of Big BIM and Little BIM is important. One of the mistakes I see engineering firms make is simply adding software that they think or they've been told makes them, quote, BIM compatible, without first considering their design process. I often hear comments like, we're doing BIM work because the architect wants it, or we're doing BIM, but it's more work for us for the same fee. Remember, BIM's not a technology, it's a process, and that moving to this new process can be made much easier with software that's designed to support your engineering workflows, not add new ones. So why now? What's driving this change to BIM? Well, from a market point of view, it's cost. Everyone wants it to be done faster and cheaper. Owners are looking to reduce cost. Firms are looking for efficiencies and to do more with less. Second is improvements in technology. Today, the software and hardware are now available to facilitate this process. This just wasn't the case a few years ago. And it's this new technology that is the focus of today's presentation. We're going to look at the essential technologies that can help consulting engineers easily plug into today's BIM workflows. In summary, we're going to discuss 4 essential technologies for structural design. First, 3D information modeling, or the ability to create intelligent 3D structural models. Here we're moving beyond lines, bars, and nodes, and designing with intelligent structural objects that understand their physical and analytical properties. Second is a concept I call bimodeling, or technology that integrates structural and analytical modeling. Traditionally, engineers are used to having their own engineering model, the analysis model, and the draftsmen are in charge of documenting the design. New structural design programs integrate these two models, so the analysis and the structural model are simply different views of the same data. This integration opens up many new possibilities and really encourages the engineer to play a more central role in the design process. Next is the integration of analysis and design with detailing. We're seeing the need to integrate these functions more closely. In fact, if you look at the latest versions of both the IBC and the Eurocodes, both are pushing for more integration. Lastly, interoperability and collaboration. Structural design programs should provide technology that make it easier for engineers to collaborate with others involved in the design and construction process. Now, let's take a moment to look at each of these technologies in a little more detail. As we said earlier, one definition of BIM is modeling. So 3D modeling capabilities are the first essential requirement for any structural design software. One of the key characteristics of a structural BIM software is the ability to model with parametric objects. Here we have a parametric frame object. To create this frame, we don't draw or model it as we would with a traditional CAD or analysis and design program, but we define the frame by defining its real-world structural properties, or parameters. In the properties dialog, you can see the properties that make up this frame: its height, the number of bays, columns, cross-sections. If you need to make it a little longer or taller or change the number of bays, you don't remodel it, you simply edit its properties by typing in new values into its dialog box. Once the frame is defined, you can easily use it to build up your design. Here we'll add the frame just as we designed it. Then we'll pull out 3 copies. Next, we'll use the same technique, but this time define a crossbeam between the frames. And once we create these parametric objects, they can be saved into a library and reused from project to project. Here you can see examples of the parametric objects we have stored in our object library. Now to finish off this demo project, we're going to grab a truss object from our library and add it to our building as part of our roof structure. Designing with parametric objects makes creating models fast and easy. And even more powerful is the ability to combine parametric objects with other objects to define and drive the design of more complex structural systems and even entire buildings. For example, here we have a steel hull. Again, this building wasn't modeled. It was designed by defining a few simple parameters. Here you can see the parameters that define this building. So if you need to make a change, you don't remodel it, you simply type in new values. For example, here we will change the building's ridge height, reduce the span of the frames, and change the number of bays. When we click OK, you can see the model is automatically updated. This idea of parametrics can be taken a step further to include design properties like load combinations, optimization settings, and other design parameters. Having the ability to add design parameters to your project can save a lot of time by automating the setup of common and repetitive design tasks. Some software companies are using this parametric modeling technology in the PEB market to drive the design, engineering, estimation, and fabrication of entire metal buildings. Tilt-up is another area where software companies are addressing the needs of the market with parametric modeling technology. It's very easy to create parametric rules to design the wall panels, for example. And precast is a vertical market that lends itself very well to parametric design. Here, precast members can be modeled parametrically to meet design codes. Then, the model can be used as the inputs for fabrication. Designing with parametric objects saves time and makes it easier for engineers to quickly explore alternatives, but you don't want to be limited to parametric design. Structural design programs need to be flexible and support things like user-definable cross-sections and free-form modeling. Your structural design software program should allow you to create custom cross-sections by importing profiles from CAD drawings, as well as allowing you to quickly sketch them out, as we're doing here. In this example, we'll give our shape a green color so you can see it a little bit better on screen. In addition, we can use Boolean operations like add and subtract to help us create just the shape that we need. For this shape, we'll clip two circles to create voids in this cross-section profile. In addition, we could add analytical properties to our profiles. For example, here we're assigning this cross-section finite element data, and we'll define the finite element mesh. With the mesh defined, you can see the FEM results. Here you can see the shear and torsional stress distributions on the profile, and we can even turn on the mesh. Once defined, we can add these new cross-sections to the program's cross-section library and then use them from project to project. In this example, we've selected a more traditional cross-section shape. Using this profile, we can quickly create the curved beams to connect the columns in this project. These cross-sections we selected are simple extrudes. However, we could easily assign different cross-section shapes at different points along the beam to make them non-prismatic. Here you can see better the shapes of my custom beams for this project. Now, with our columns connected, we'll use the modeling tools to add curved shells between the beams to form the roof. Next, by duplicating and arraying the beams and shells, we can quickly connect the rest of the columns to finish our structure. And here you can see our Antonio Gaudí inspired model, which is now ready for loading and analysis. But most of all, modeling needs to be easy. You always need to be able to get in and quickly sketch out your bars and nodes as you would in any traditional A&D program. We'll start this project by sketching out a parabolic curve. Next, using familiar editing commands, we can duplicate the curve to create a series of arches. Then, using the curve from the arches, we'll add a shell. Pretty simple. To finish off this design, we'll add some gable end columns. Then extend the columns to the top of the arch. Note when we extend the studs, they automatically trim correctly. Lastly, using traditional modeling tools, we'll add an entry. Here, we'll sketch the shape for our entry, extrude the shape, then clip the extrude to create the opening and the entryway structure. And now our model is ready for loading and analysis. Very fast, very easy. The second essential technology in structural BIM is the integration of modeling and analysis, or what I call BI modeling.